Okay, welcome to office hours for the robotics MOOC Ludobots, hosted out of Reddit. For those of you that are new to the course, you can get started at any time by following the URL pointed to there. This is also office hours for the University of Vermont course CS206, Evolutionary Robotics. I will be online from now until 4 p.m. Eastern Standard Time. If you have any questions about the course, or robotics and AI in general, I'm happy to answer them. Please ask your questions at any time. In the meantime, I will talk a little bit about the final project ideas. So to find out more about final projects, let me show you how to navigate there. Okay, so as I mentioned, this is the robotics MOOC Ludobots. This is where we're hosted, and you'll notice for the newcomers at the top, there is a link called New, Start Here. You can click here, and the comment here has a lot of links to various aspects of the course. The one we're most interested in today is the schedule. So just to start at the home page again, click on New, Start Here. Click on Schedule, and you can see where we are in terms of the course as a whole. Okay, so this is, we are now working our way through a history of the course. Working our way through a history of the course, and we just finished last week our discussion of the minimal cognition experiments. This week we will be moving on to active categorical perception and early experiments in legged locomotion with robotics. So we have completed lectures 1 through 9. There are video recordings of all of those lectures if you want to try and catch up to us. There is also all of the reading available here. Okay, for the graduate students who are taking the course, they have finished all 10 assignments and they are now moving on to the first deliverable of the final project. So some of the UVM students are now working on their final projects. Other of the UVM students are still working their way through the assignments. So before we talk about the final project, let's talk about these assignments. Let me just back up again to the main page of the course. If you're interested in finding these projects, again, click on New, Start Here. And again, from the schedule, you can find links to all of the assignments starting for the first week. Here's the link for assignment 1, assignment 2, and so on. Okay, so if you click on, for example, assignment 1, that will take you to a Google document which gives you a very brief summary of what you're going to be working on. And then from there, it'll take you back to Reddit where the actual instructions for the assignment can be found. Okay, so that's a little bit about the assignments. Let's talk about the final project. Again, let's back up to the, I'm sorry, one other thing I wanted to talk about the assignments. So let's go back to the assignments for a moment. All right, as again, the assignments are all linked from the schedule, and the assignments themselves are embedded in Reddit. And you'll notice we're following the Python-only track. There are a number of projects leading all the way up to the last project, which is phototaxis. So for the online students, if you're following along at your own pace, when you finish the phototaxis experiment, or when you finish the phototaxis assignment, you will have a robot evolving on your computer that is attempting to move towards this light source that's placed several body lengths in front of the robot. Okay, so at the end of this assignment, phototaxis, you have a basic evolutionary robotics simulation, and the final project is to then take this basic simulation and expand it in any direction you like to investigate some question about robotics or AI, and it's up to you what you might like to tackle. If we go back to the home page for the course, you'll see there's a new link up here called Final Project Instructions. So there's instructions about the final project as well as a bunch of final project ideas. So if we click on Final Project, it'll take you through to, again, a Google document with all the information. The first few bullet points here are for the UVM students. So for the online students, you can ignore that, and you can move right on to looking at various project ideas, and we'll walk through some of those today. So again, these are just some ideas that were proposed by students in the past that I think are doable with the basic evolutionary robotics simulation you're building in this course. Again, you feel free to come up with any idea you like. I put in here a link to the robotics subreddit. There's hundreds and hundreds of cool robots on there. Some of them might inspire you to try and create a simulation of those robots and then evolve them to do something interesting. Okay, let me show you a few projects that have been tackled in the past. Let's start with a WEGED robot. This is work by Owen Marshall here at the University of Vermont. You can see Owen's wheeled robot, WEGed robot here. As the name implies, a WEGed robot is capable, has both legs and wheels. I will try and pause the simulation and maximize it for you so you can see a little bit better. So we can see that Owen has created this hexapedal robot with 3 legs on the left, 3 legs on the right, an upper leg and a lower leg, and then each leg is tipped with a wheel. And this robot has been evolved to get over the barrier in front of it, and you can see that it's using both its wheels and its legs, and it's evolved an interesting behavior, which is to tip backwards, hit the barrier, and then sort of roll up and over the barrier. An interesting use of the combination of wheels and legs. So an interesting project might be, first of all, to create such a robot in the simulation, evolve a behavior for it, and then ask some interesting scientific question about this robot. For example, what kinds of environments might a WEGED robot do better in than either just a wheeled robot or just a legged robot? This particular project, I think, is relatively well-timed because Boston Dynamics recently released sorry, there we go. Boston Dynamics recently released a video of its own WEGED robot, which I would imagine, if you're interested in robotics, many of you have already seen. This is Handle in operation here. Notice Handle is one kind of a WEGED robot. Again, it would be interesting to try and create a simulation of just this robot and then see what kinds of behaviors you could evolve for it. Okay, this would be a perfectly reasonable robot to try and simulate and then evolve behaviors for. Okay, so that's a WEGed robot. What else might you tackle? Well, you might try evolving bipedal robots. Bipedal robots are tricky because they're inherently unstable. This is an example of a simulation I created years ago. Not the best bipedal locomotor you've ever seen, but you get the basic idea. So it was an attempt to try and use the upper body of the robot to help stabilize itself. I would count this as a qualified success, let's say. So bipedal locomotion is pretty tricky, but not impossible. Okay, just a reminder for those of you that are joining us, these are the office hours for the Ludobots Robotics MOOC. Please ask any questions you have at any time. I'm happy to answer them. While I'm waiting for a question, I'm just talking you through ideas for final projects. Okay, so we looked at a WEGED robot, a biped robot. Some of you might be interested in collective intelligence. So this was just a fun simulation we put together a while ago to simulate a bunch of robots, a swarm of robots that are attempting to move this red bar in their environment, and as you can see, they're not doing a very good job at it. Okay, again, something that's possible in the simulator. What sorts of things might you do with a robot swarm? Well, one of the things that's interesting about collective behavior is trying to evolve robots that do something together that's beyond the ability of any one of them to do on their own. So a question you could ask once you're able to simulate and evolve a robot swarm is, what kinds of tasks might those be? Okay. Last week we discussed the minimal cognition experiments. And we talked about different aspects of cognition. So, for example, what about selective attention? This is one aspect of intelligence. And this is a video from David Buckingham, a former student here at UVM. This was a re-implementation of Randall Beer's minimal cognition experiment. And this video, I think, captures exactly what selective attention is. You need to have a robot that can selectively attend to one or other of the objects in its environment. This is a challenging task, as you can see, because the robot can't always see both objects at the same time. Not only that, but it has to decide which object is going to hit the ground first, go and collect that object, and then once it has collected that object, it has to remember where the other object is and get to its final position in time. This is a pretty challenging task. You can see that David managed to successfully evolve a wheeled robot that succeeds at selective attention. You might try and replicate this experiment and then perhaps change the wheeled robot into a legged robot, which would be much more challenging. Okay. So that's legged robots, biped robots, robot swarms, robots that exhibit some building block of intelligence like selective attention. Another very popular project, as you might imagine, is evolving predator and prey robots. Here's was one attempt to do this. Oh, I'm sorry. Let's see. Here's the video. So here's an example of an attempt to try and evolve a predator robot and a prey robot. You can see the red robot is the predator, and it's trying to minimize its distance to the prey robot in green. And the fitness function of the prey robot is, as you can imagine, the inverse, which is to maximize the distance from the predator robot. So we have two robots that have different fitness functions, and is one or the other able to evolve the ability to outcompete the other. Okay, another popular project is to try and evolve some aspect of the body of the robot along with its artificial neural network or brain. I talked about this last week in class, or I'm sorry, I talked about this in office hours last week. And actually, if you go back to the schedule for the course, you'll notice that I've actually put up I taped office hours from last week, and they're available online as a video. So you can go and watch last week's office hours, and and there I coded up an evolutionary algorithm that was able to evolve both the body of the robot along with its brain. Okay. This is evolving bodies and brains of robots has a relatively long history. It dates all the way back to the early 1990s by some work by Carl Sims. This was exceedingly impressive at the time, given the computer technology back then. But you can see that Carl was able to evolve some pretty sophisticated robots that were able to swim and run and jump and so on. If you go Google Carl Sims, you can find this video and watch his menagerie of different robots. So again, this is one of the interesting aspects of evolutionary algorithms compared to machine learning. So in machine learning, or learning in general, as the name implies, learning is tuning just the brain of the robot. But evolution is not restricted to just tuning the brain. It's able to tune or sculpt the body of the robot along with its brain. And I think that's sort of the long-term potential for the field of evolutionary robotics. Okay, so that was some work done back in the early 1990s. There's been a lot of attempts to improve upon Carl's original work. This is a more recent attempt, which is quite impressive. Was presented back in 2013. This was using a relatively fixed morphology, but the actual muscle placements were evolved, and you can see the evolutionary process here changing the muscle placement. Which produces interesting gaits for robots with different bodies. Okay, again, there's some keywords if you want to go Google this video and watch the remainder of it. Pretty impressive work for the time. Okay, a project like this obviously is probably a little bit too ambitious for this course, but you might be able to come up with a simplified version of this project to tackle. Okay, so that was evolving bodies and brains. You might try and create a robot and evolve it to produce a behavior other than walking. For example, brachiation. This is again a project I was involved in several years ago. There's the URL for an early version of Ludobots. You can see I'm creating some metal bars between the robot and its food source. So the robot is evolving to minimize its distance to this object over here. And you can see it's evolved some form of brachiation, which in primates is swinging from tree branch to tree branch. I'll show you this video again. You're actually watching me build the robot in the simulation itself. Okay, again, like bipedal locomotion or evolving bodies and brains, this is a pretty challenging project, but not impossible. I think this is doable in a month or 2 months of work. Okay, that's brachiation. Other ideas, active balance control. This is a little bit of an easier project, I would say. When this comes up, this is a video of a physical robot doing active balance control. As you can see, it's trying to maintain a horizontal stance for its main body on uneven terrain. This is active balance control. I would say that this would be a relatively straightforward project. Okay, another one that I always throw out every year and no one's been able to tackle yet is evolving a robot capable of simultaneously grasping multiple objects. This is a picture, not a simulation. No one's been able to simulate this robot yet. You can probably see why. It's got a very complex morphology. Its morphology is fractal. So this is a robot arm, if you like, and at the end of every arm are 3 smaller arms or fingers. If you were to create a simplified version of this robot, perhaps not to the fractal depth you see here, you could imagine that this robot might be capable of things that are beyond robots that have a human-like or animal-like form. This particular robot, as you can see in this image, at least in theory, should be able to simultaneously grasp and manipulate a large number of objects. Okay, again, that would be pretty challenging, but I would love a student to try and tackle that one. So if you're interested, please consider it. Okay, let's see. And again, I mentioned a good source of ideas is the Reddit, the robotics subreddit. Which is apparently suffering a fair bit of load at the moment. There we go. Okay, so if you go to the subreddit here and click on top, you can see the top posts from all time, and you can sort of scroll through here. Most of these are videos. Have a look at some of these robots, and you might try and create a simplified simulation of them. Okay. Okay, once you do come up with an idea for your final project, you can create a post in the online course and point other students to your project as you work on it. And I'm going to show you how to do that now. So let's go back to the home page for the course. Okay, let's go. So here we are, and let's say that I have an idea for a project. So I'm going to submit a new link. And let's imagine that I started to sketch out the idea for my project in a Google Doc or some other document online, if I can. Okay, so here I am back at the online course, and I have a Google Doc where I'm going to start to write out ideas for my project here. I'm going to take the URL of this project, of this document. I'm going to go back to the online course, submit the Google Doc, and I'm going to give my submission a tag, which is project idea. So my tag is project, and my project idea is compare a legged robot to a legged and a wheeled robot. So I want to try the legged project, submit my project, and it'll show up on the main page of the online course, I hope. It may be that I've submitted too often here, so I can't see it at the moment. Ah, there it is. Okay, so here's my project, compare a legged robot to a legged and a wheeled robot. So I click on this, and this takes me to my Google Doc. And then over the next month or two, I can start to flesh this out. My project, so my hypothesis, and let's start with a hypothesis. My hypothesis is that there exists an environment, or set of environments, in which a legged robot can outperform both an equivalent legged robot and an equivalent wheeled robot. Okay, so there's my hypothesis. That's what I'd like to test. Now I need to do a little bit of experimental design. So how am I going to actually reach this endpoint of creating this? Well, I'm going to break this down into a series of bite-sized chunks or deliverables. So let's create a list of deliverables. Okay, first deliverable is take the quadruped and put wheels on it. So if we go back again to the course, you'll remember that at the end of the last assignment, so if I just skip to the assignments here, you remember at the end of the assignments you have a quadruped which is being evolved by a genetic algorithm to exhibit phototaxis. And here's our quadruped in action. So I already have a legged robot. Okay. So my idea is going to be to put wheels on the bottom of these legs. That's the first thing I'm going to do. Take the quadruped and put wheels on it. And then demonstrate the quadruped in 3 modes. So wheeled mode, lock the legs, and evolve wheeled movement. So in the simulation, I can take objects that are attached together by a rotational joint, like the elbows and the knees and shoulders of my robot, and I can limit the range of motion to be very, very narrow, so plus or minus 0.0001, and I'm basically locking the wheels straight and only allowing the wheels to spin. So that's using the same robot in wheeled mode. Then I can use it in wheeled mode, where now I lock the wheels and evolve legged movement. And the same robot, I then unlock both and evolve wegged locomotion. So I'm breaking my hypothesis down into these bite-sized chunks. So I'm altering my simulation in such a way that I can evolve behaviors for a wheeled robot, a legged robot, and a wegged robot, where it's really the same robot, just with some subset of its joints or wheels locked. Okay. Demonstrate the quadruped in these three modes, and then create an obstacle in front of the robot for it to overcome. So let's imagine that's the first environment I want to try out. So if we go back to Owen's wegged robot, you can see that there is this obstacle in front of it, and it evolves the ability to get up and over it. So this was a good choice of an environment that's a little challenging for just wheeled or legged robots. This wegged robot kind of uses the wheels to drive up the front side of the obstacle and then over. Yeah. Okay. Okay, so I've broken it down into these three situations, and now perform a set of evolutionary trials as follows. Let's do 30 trials of the genetic algorithm using the wheeled robot. I put wheels in quote because it's all the same robot, it's just that the legs are locked in this case. Perform 30 trials of the genetic algorithm using the legged robot. So another 30 runs. And then finally we do, or 30 trials, and finally we do a third set of 30 trials of the genetic algorithm using the full wegged robot. And we can then analyze the best of these 90 robots. So at the end of each evolutionary trial, we have the robot that got the furthest, right? Maybe it got over the barrier, maybe it didn't. And try and answer the question, on average, did the wegged robot, let's put this in another line, on average, did the wegged robot do better than either the wheeled or legged robot? Okay. If it did not, choose another environment. So in other words, go to step 3, which is where we chose the first environment that had this obstacle in front of the robot. Maybe rough terrain would be a better environment to really show off the advantages of a wegged robot over a wheeled or legged robot. Okay. Okay, if it doesn't, then we're done. If it did, then we have supported our hypothesis. In other words, we found an environment in which the wegged robot does better than either the legged or wheeled robot. So I've taken a project idea, so this sort of wegged robot. I've come up with a hypothesis or a question I would like to test using that robot, and I've then broken that down into a series of deliverables and done each one as we go. So remember that this Google Doc that I've been working on is linked to from the course. You've created a submission, so you have your own project stub here in the course itself. So here's my, here's my project stub right here. Compare a wegged robot to a legged and wheeled robot. So as you work on this project over weeks or even months, again, it's up to you. You're free to work at your own pace. You're going to start to fill in this document, right? So maybe after you finish the first deliverable, where you take the quadruped and put wheels on it, you create a short video of this robot in operation, and you create a link to that video so that people can follow that link and see that you've implemented that step. Maybe you add some instructions so that another student who wants to try and build on your project follows your instructions. So first, create a new create a new cylinder that will act as the front left wheel, dot, dot, dot. Then create the front right wheel, dot, 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 and so on. So you're basically, as you're creating these deliverables, you're fleshing them out by writing instructions to really explain how to implement this particular deliverable. And you can tell how good these instructions are by trying to view these instructions as a new student to the course who's completed all of the assignments and is now deciding whether to, and is now trying to implement your project, right? And like in the projects that you've just completed, as the student follows these instructions, you might have links to pictures and screenshots and equations if necessary, or little snippets of code to help them along. Okay. Okay, I think that just about does it for the final project. Again, these are the office hours for the Ludobots Robotics MOOC. If anybody has any questions, please go ahead and ask them. I mentioned that I would talk about final project ideas. We have about a half an hour left. I'm happy to talk about any questions from the course or robotics in general. Until then, I will just hang out here online and wait in case there are any questions. Okay, since there don't seem to be any questions for the moment, I thought I'd show you some other aspects of the simulation that have not yet come up in the course. We were just talking about a WEG'd robot, which is a combination of wheels and legs. So if you actually look in the PyroSim directory, you'll find that there's a demo here called car. So let's have a look at, let me run this demo first. Demo 16. And you'll notice this is a pretty, just about as minimal car as you can get. We've got a main body and a single wheel. And I'm going to show you how to actually simulate this wheel by looking at the code that makes up this demo. Okay, before we look at the code, you'll notice that the wheel operates as a wheel should, that it's turning at a constant velocity. So up until now, we've been seeing robots in which the upper and lower leg, for example, is attached by a rotational hinge joint. And the neural network, or the brain of the robot, dictates the desired angle of that hinge joint. So that's position control, meaning the neural network or the neural controller is dictating the desired position or desired angle, in this case, of the joint. When we simulate a car or wheels, we're going to switch from position control, so dictating the desired position or angle of a joint, to a desired velocity, right? So maybe the neural network dictates this speed of rotation of the wheel or this speed of rotation, or this speed of rotation. So let's have a look now at the demo to see how this is done. Okay, so let's work our way through this code here. It's pretty straightforward. As usual, we create an empty virtual world for our robot to inhabit. We then send a single cylinder. You'll notice that the cylinder has 0 length. All of the cylinders in PyroSim are capped cylinders, so they have a semisphere on either end. Obviously, if we have a capped cylinder of length 0, we have a sphere, which is going to be our wheel, and we need to give that wheel a radius, and we place it into the environment, and it has an object ID of 0. We then add a box, which is the main body of the car in this case, and now we define a joint. It's the first joint, so it has an ID of 0. It connects the wheel to the main body. We give that joint an X, Y, and Z position. This is the position at which the wheel attaches to the main body, the axle, if you like, of the wheel. We give this joint a joint normal as usual. So this is the normal that is now going to dictate around the axis around which the wheel spins. So you can think of this vector, the joint normal, as the axle of the wheel. We're giving it a low and high velocity. This is currently expressed in angles. Doesn't really matter. It could be low of -10 or +10. Let's actually change it here. Let's speed up our wheel a little bit. -10 and +10. And you'll notice the last argument you haven't seen before. This is position control. So again, the default when you create a joint is to use position control, which is that the neural controller dictates desired position or desired angle of the joint. We're turning off position control. When you turn off position control, we get velocity control. So now the neuron is just going to dictate the desired velocity rather than the desired position. Okay. Everything else is as normal. We create, in this case, a touch sensor, which is put inside of object 0. The wheel. We place a sensor neuron and connect that sensor neuron to our only sensor, the touch sensor. We then create a motor neuron, and that motor neuron attaches to the only joint, which is the joint that connects the wheel to the car. And we send a synapse. We create a synapse that connects the only sensor neuron to the only motor neuron and give it a weight of 1. And then start the simulation. Okay. You'll notice I made a slight change to this code, which is I've expanded the minimum and maximum possible velocity. Let's see what happens now. Okay, we have a unstable simulation. You can see that this speed is much too fast for our car here. Getting some interesting car acrobatics here. So let's slow the minimum and maximum possible velocity of our wheel. Still not great. Let's try and slow it down even more. All right, that looks better. Okay, so again, I've only added one wheel here for you. You can take demo 16 and add the other 3 wheels and create a true car. Okay, what happens if we invert the weight of this synapse? So now we're still connecting the only sensor neuron to the only motor neuron, but we now are connecting it with a weight of -1. One way to know whether you're building up an intuition for how the simulation works is to make some of these changes in the code and make a prediction about how the robot will behave. Let's run this now. And as hopefully you predicted, the wheel is now turning backwards, right? There is a touch sensor inside this wheel. It's firing. so its value is 1.0. The synapse has a weight of -1, so that's being sent to the motor neuron. So the motor neuron is outputting a value of -1. And that's interpreted as a desired velocity of -1 radian per second, right? So turning in the opposite or the backward direction. Okay, so that's how to use wheels. The only real difference you need to make is to, when you create a joint, is to turn off position control, which means you're now operating with velocity control. And the low and high are now not the minimum and maximum possible, now is not the minimum and maximum possible angle or position of the joint, but the minimum and maximum possible velocity of the wheel. So by creating multiple joints, some of them which have position control turned on and some of them which have position control turned off, you can create a WEGed robot, which is a combination of legs and wheels. Okay. Again, we've got about 15 minutes left, so if anybody has any questions, please go ahead and ask them. I'm happy to try and answer. Okay, since we've got a few minutes left, I thought I would continue talking about some of the other aspects of PyroSim that might be of interest to you as you're pursuing your project. As we've seen, let's see, as we've seen before, you can create relatively simple simulations of robots where a robot is made up of multiple objects that are attached together. In some cases, you may want to weld some of the objects to the world and make them immobile. So for example, if you're creating a robot arm, you might want to make the base of the arm welded to the ground. You can do that using fixed objects. So you'll notice there's another demo in PyroSim called Fixed Objects. And if I open this demo here, you'll notice that we are still creating the robot arm. It's made up of two cylinders, the upper and the lower arm. We then connect those two objects together, object 0 and object 1, and allow it through position control to move. We then create a second joint which connects the first object with ID 0, which is the lower arm. We attach it to a second object which has a -1 for its ID number, and there are no objects here that have an ID of -1. The -1 means the world. So what this really means is attach the lower arm to the world with a given position. Actually, the position doesn't matter because this object is never going to move. Okay, so let's play the first one again where both objects are free to move. And we have a robot that can sort of move freely about its environment. Now when we run demo 17 with a fixed object, we see instead that the lower arm is attached to the world. Right? And it's only the upper arm that's able to move. Okay, so for those of you that are putting obstacles in your robot's environment, or you want to simulate a robot arm, you can do so by creating fixed objects by welding that object to the world, which is specified by providing an object ID of -1. Okay, again, those of you who are just joining us, this is office hours for the robotics MOOC called Ludobots. You can find us at our own subreddit listed here. If you this is office hours, it's going to run for another 10 minutes or so. Kind of quiet today. Most of the students here at the University of Vermont are working on their final projects. I've shown that if you go to our homepage here, you can see there are several final project ideas for those of you that want to try and tackle your own final project. If you have any questions about that, I'm happy to answer them. While we're waiting, let me talk about next time. So next week, I will introduce a new evolutionary algorithm, at least new to the course, which is multi-objective optimization. So maybe I can just talk a little bit about this to set things up for next week. Everything you've been doing so far in this course has been using a single objective. You've been trying to get your robot to succeed at one objective, which up till now has just been movement into the screen, or in the case of the phototaxis project, moving towards a light source in the environment. But in most real-world robotics applications, we want to try and optimize our robot to succeed at multiple objectives. So for example, we may want our robot to move in as straight a line as possible. That's one objective. Second objective might be move as quickly as possible. Third objective might be move with in the most energy efficient manner as possible. So we might try and optimize straightness of path, velocity, and energy efficiency. How do we get a robot, how do we evolve populations of robots to improve not just one of these objectives, but all three or all K objectives at the same time? Well, in order to do so, we have to create a multi-objective optimization. So what I'll do next week, if there aren't any questions, is I'll take the standard genetic algorithm that you've implemented in this course so far and expand that genetic algorithm into a multi-objective optimization method. If you like, between now and next week, you can read up on what multi-objective optimization is, and then I will code it up within the hour, assuming we have enough time. So if you want to follow along with me, make sure that you finish the genetic algorithm project, and I'll walk you through turning the genetic algorithm into a multi-objective optimization algorithm. Okay, we just have a few minutes left, so I will introduce just one last aspect of PyroSim, which you haven't seen so far. So far in the course, you've implemented a number of sensors. You've used touch sensors, which report whether the object in which the touch sensor is placed if that object is touching another object or not. We've seen proprioceptive sensors, which report the current angle between the two objects. So a proprioceptive sensor is embedded in the joint that connects pairs of objects together and reports those angles. We've also seen the ray sensor, which emits a ray out of an object, and if that ray collides with another object, it reports the length of that beam. So ray sensors give your robot an ability to see the world around them. There are other sensors you can create. So for example, the vestibular sensor here, this is not unlike your own inner ear, which reports how your head is oriented relative to to gravity. So if you place a vestibular sensor in an object which is perfectly horizontal, as that object starts to drift away from, let's take a rectangular solid here, as it starts to drift away from horizontal, that value will increase above 0 or decrease below 0. So when the vestibular sensor is reporting a value of 0, that means that the object is horizontal. Okay, so that's a possible sensor that can be used. Let's see, what other sensors have we not talked about? Oh, we also talked about position sensors, which report the X, Y, and Z position of the object in which the position sensor is attached. We've talked about proprioceptive sensors, ray sensors, touch sensors, vestibular sensors. Light sensors, that came up in the phototaxis project, so we talked about that. I think that may have covered all of the sensors so far. Yeah, I think so. Okay. Okay, so we only have 5 minutes left, and it seems that there aren't any questions for today, so I think we'll stop here for today. Again, thanks to those of you that tuned in. Next week, as I mentioned, I will walk you through how to code up a more high-powered evolutionary algorithm than the genetic algorithm, which is multi-objective optimization. So we will see you then, and again, thanks for attending today.